Imagine standing on the floor of the Pacific, 6 kilometers down. Above you sits a column of water so heavy, it is like having an Abrams tank parked on every single square inch of your body. At 8,500 pounds per square inch, the environment is not just dark, it is a physical hammer. Most materials we use to build our world would simply give up and fold under the weight. But for the March 2026 mission to the Clarion-Clipperton Zone, engineers had to build a camera that doesn't just survive this weight, it has to remain perfectly still to capture the secrets of the deep. The first line of defense is a material that sounds fragile but is actually a beast of engineering. Sapphire. Not the gem in a ring, but a lab-grown monocrystalline alumina lens. Sapphire has a compressive strength that dwarfs standard glass. While a normal window would shatter instantly, this crystalline structure can handle the weight of a mountain without flinching. But there's a catch. Sapphire is so hard it's brittle. If the mounting isn't perfectly flush, even a microscopic grain of sand could cause the whole lens to explode into dust. To prevent that explosion, engineers use a technique called auto-frettage. They pre-stress the metal housing, essentially squeezing the camera before it ever touches the water. This creates a state of equilibrium. When the ocean tries to crush the camera, it's actually fighting against the internal tension the engineers built in at the factory. It's a clever bit of physics that turns the ocean's greatest weapon, its weight, into a stabilizing force for the camera's structural integrity. Even with sapphire and pre-stressed titanium, there is a weak point. The seals. Water at this depth can find its way through any gap, no matter how small. If a single drop of salt water touches the internal electronics, it's game over. The camera would short circuit and die in a fraction of a second. This is why the 2026 mission relies on a revolutionary sealing architecture, known as the Leviathan system. It doesn't just block water, it uses the pressure to seal itself tighter. The Clarion-Clipperton Zone is one of the most remote places on Earth. It's a vast plain of abyssal mud, thousands of miles from the nearest coastline. The mission's goal is to document the unique life forms that live among the polymetallic nodules, small potato-sized rocks that contain the minerals needed for our green energy future. But to see them, we need to solve the greatest engineering challenge of all: how to move a camera in a place where the air itself would be a liquid. The heart of the Leviathan system is a dual redundant mechanical face seal. Think of it like two highly polished ceramic rings rubbing against each other with zero gap. These rings are polished to within a few light wavelengths of flatness. They are so smooth that water molecules literally cannot find a way between them. And here is the genius part. The deeper the camera goes, the harder the ocean pushes the rings together, making the seal even more effective at 6,000 meters than it is at the surface. But the seals aren't alone. The entire camera housing is filled with a special non-conductive silicone oil. This is called a pressure-balanced oil-filled system, or PBOF. Because liquids are incompressible, the oil inside the camera pushes back against the ocean with the exact same force. It's like trying to crush a balloon filled with water. It's nearly impossible. This allows the titanium walls to be much thinner and lighter than if they were holding back the pressure alone. It's a masterclass in working with physics instead of against it. The oil also serves a second purpose: cooling. At the bottom of the ocean, the water is a chilly 2 degrees Celsius, but the camera's high-speed processors generate intense heat. The silicone oil acts as a heat sink, pulling warmth away from the electronics and transferring it to the titanium shell, which is then cooled by the freezing abyss outside. It's a perfectly closed loop. No fans, no moving parts, just pure material science keeping the brain of the camera fermenting while it's surrounded by ice-cold water. But how do you get the video signal out? You can't just drill a hole for a cable. That would create a leak path that the pressure would exploit instantly. Engineers use glass-to-metal seals. The electrical pins are encased in a special glass that is melted directly into the titanium connector. It becomes a single solid piece of matter. There are no gaps, no O-rings. The atoms of the glass and the atoms of the metal are bonded together, creating a barrier that is literally as strong as the wall itself. To ensure everything works, the camera is placed in a hyperbaric test chamber. They ramp the pressure up to 10,000 PSI, well beyond what it will face in the Clarion-Clipperton Zone. Engineers listen for acoustic emissions, the sound of the metal microscopically groaning. If they hear a pop, it means a structural flaw is present. Once it passes this pressure torture, the camera is ready for the abyss. It has been forged in the most extreme conditions humanity can create on land. The environment at 6,000 meters is often described as a physical void. It is a place where light from the sun has never reached and the temperature never changes. In this void, the camera's lights are the only thing that matters, but even light behaves differently here. The water is so dense it absorbs colors, starting with red. To capture the true colors of the deep-sea life, the 2026 camera uses ultra-high CRI LEDs that oversaturate the red spectrum to compensate for the water's filtering effect. Data transmission from the bottom of the ocean is the final hurdle. Radio waves don't travel through saltwater. Your Wi-Fi would die in centimeters. The camera is tethered to a surface ship by a fiber optic cable thinner than a human hair, reinforced with Kevlar. This is the camera's umbilical cord to the world above. Through this tiny thread, 4K video data travels at the speed of light, allowing scientists on the surface to see the abyss in real time for the first time in history. The impact of this engineering is profound. By seeing the Clarion-Clipperton Zone clearly, we can understand the delicate ecosystem that lives on these mineral-rich plains. We are discovering species that look like they belong on another planet, creatures that have evolved to thrive in a world of crushing weight and eternal night. The camera isn't just a tool for observation, it's a witness to a part of our planet that has remained hidden for 4 billion years. The technology developed for this mission, the Sapphire lenses, the Leviathan seals, the PBOF systems, is already finding its way into other industries. From high-pressure chemical reactors to the next generation of space probes bound for the icy moons of Jupiter, these engineering solutions are expanding our reach. It turns out that learning how to survive the bottom of our own ocean is the perfect training ground for exploring the rest of the solar system. Next time you look at a simple camera lens, remember the sapphire window that can hold back the weight of the Pacific Ocean. Behind every frame of video from the deep is a symphony of mechanical engineering, material science, and pure human curiosity. The abyss is no longer a void. It is a place of wonder, brought into the light by the most resilient machines we have ever built.